Hello. So in this new episode, we'll together discuss a paper called "Bidding with Securities, Auctions and Security Design." Okay, so which is written by DeMarzo et al. In 2002. So basically, what they're talking about in this paper is they're trying to provide a new approach to allow se- the bidders to use securities to make their bids in the auctions. Okay, either first price auction or second price auctions, and they studied some very interesting properties and got some very nice results from that. Okay, so instead of bidding with cash, okay, so the securities here refer to something like the equities or debts or call options. So they all represent some part of the partial future, the part of the future cash flows. Okay, so instead of paying in cash, so that's essentially what this paper is talking about. Okay, so let's together take a look at this paper. Okay, so they gave a very good example in the beginning. Okay, so let's review that example first. So let's use their example. Okay, so consider an auction. So there are two bidders. Okay, Alice and Bob. Okay, okay, so two people here. So they are competing for this project. Okay, so there are two buyers and one seller. Right. So the project it needs a initial fixed investment. So in this example, it will be 1 million. Okay, so there's a $1 million fixed initial investment. Okay, so this doesn't matter too much. Okay, it's just a fixed number. So Alice thinks that if she can take the project, then on average, this project can give Alice a future cash flow of $4 million. Okay, so let's put it somewhere else. Okay, okay. So let's say Alice has a. So this is something that we call as the private value, right? So in an auction, so Alice thinks that she can get 4 million from the project in terms of the future cash flow. Okay, so that's the value of this project for Alice. But Bob thinks it just gives him $3 million. Okay, so those are some private values, right? As we just said, and so let's suppose that this is a standard second price auction, and we all know that, and in previous episodes we know that it's a it's a dominant strategy, right, for the bidders to bid their private values. So as a result, so if they have to use cash, okay, so this means that Alice will bid 4 minus 1. Okay, so 1 million is already some like fixed amount investment that they have to pay, right? So Alice essentially pays like 4 minus 1 is 3 millions. Okay, $1 million, and Bob pays 3 minus 1 is $2 million. Okay, so now that's the basic setting of the second price auction with cash. But here, if we allow the bidders to use something instead of cash, okay, so here we should notice that if we allow the bidders to use some like one certain kind of security, then that auction is called the formal auction, right? So because the seller already limited the range or limited the types of the securities that the bidders can use, right? So that's what we call the formal auction. But if the bidders actually do not put any limit or do not put any restrictions on the kinds of securities that the bidders can use, then in this case we call that informal auction, right? So in this case the example is pretty simple. So simply refers to the formal auction, that the bidders they use the same kind of securities. Okay, so specifically, we suppose that instead of using cash, the bidders they can just offer a fraction or a portion of their future income revenues on this project. Okay, so and here we take something as given is that their dominant strategy, if they're using this kind of equity or this kind of fraction of the future revenues as their bids, it's still a dominant strategy for the bidders to bid their private values or reservation values, right? So that's something we take as given, but we will prove that later shortly. Okay, so that's just something we use in the example. So let's say that instead of cash, Alice, in this case, it's right here. So Alice will offers 3/4, so 3/4 of the future cash flows, right? Because 3/4, that's how we get this. Okay, but Bob obviously only offers 2/3 as the fraction of the future cash flow, right, to the buyer, to the seller. Okay, so as a result, because Alice offers a higher portion, okay, and Alice wins the auction, but only pays the second highest bid. That means that Alice pays actually 2/3 amount of the future cash flow, right? So actually, finally, this means that it yields a higher payoff for the seller. So how do we see that? It's simple. We simply use 2/3 multiply by 4 million, right? Because here, why we're using 4 here instead of 3? So because in the from the perspective of Alice, Alice thinks that this project can give herself the $4 million, okay, in terms of the future cash flow. Okay, so but this bid is using the second highest bid, which is only the smaller portion, smaller fraction, which is 2/3. Okay, so we use those two to get the final payoff for the seller. Okay, and this is roughly 2.67 million. Okay, all right, but if they use cash, okay, obviously what the seller can get is only this number 2 million, right? Because Alice is paying only using cash, so it's just 2 here, right? So there's nothing else. Okay, so that's the basic idea of this example, to show that using some securities can actually improve the revenues or the payoffs for the seller. Okay, that's a good thing for the seller, but of course that's something not good for the for the for the buyer, right? For the bidders. Okay. All right. So that's a very good example, and now we continue on the model part. Okay, and we will try to briefly introduce the model of the security design problem. Okay. So there are n risk neutral bidders. Okay. Risk neutral bidders. Okay, so they are bidding for a competition on an asset. So the winner is required to make a investment, as we said, like $1 million investment, right? So X, a positive number. Okay, so this is like a minimum amount of the cash that the seller must raise, right? Must have. So X is all the same to is same to all the bidders. Okay, so that's some constant number. It doesn't matter actually. That doesn't matter too much, but we'll normalize that. Okay, so conditional on being taken by bidder I for this project can yield a stochastic future payoff Zi. Okay, this is a random or stochastic future payoff. Okay, so that's something very important. And bidders, they have some private signals, okay, regarding Z. So their signals are just drawn from some distribution. Okay, so we define that signal as Vi. Okay, good. So the seller is also risk neutral. So there's no other risk preferences in those problems, and the seller cannot take the project by themselves. Okay, so the seller has to sell this project for someone else, for the bidders to run the project. So the interest rate is normalized to 0, and we don't need to care about that. So there are some basic assumptions about those distributions. In their assumption A, okay, so they mentioned that there's some requirements for the signals and the payoffs. Okay, so basically saying that the Vi are IID, okay, and secondly, conditional on this V, then this payoff Zi has some density, has some distribution, okay, and we use H to denote that, Hz over conditional on Vi, okay, and it has a support from 0 to infinity. Okay, so and thirdly, this tuple Zi and Vi, okay, they have some property called monotone likelihood ratio property, or in short, SMLRP. Okay, so that means the distribution of Z given V. Okay, so this ratio, so that over Hz given V prime, so this ratio is increasing in Z if the V in the numerator is bigger than the V in the denominator. Okay, so that's how they define, or how they make this assumption on the on this distribution of H regarding the monotone likelihood ratio. Okay, so actually this monotone likelihood ratio property, it doesn't have this kind of requirement on the random variable here after the those conditions, right? Actually, it's just a property between those two distributions, right? So, namely, if we want to graphically show this, right? So this is the random variable, and this is the PDF. Okay, so if we have something like some PDF like this, okay, and we have something like this. So here, what we can say for those two distributions is that the upper one, okay, we can let it to be the one in the numerator, okay, and this one to be the one in the denominator. So actually, it doesn't. This should be Z, okay, and they just define that to be to satisfy this property. And actually, this property doesn't have to be some conditional distribution, right? It could be unconditional. It's just they use those to define two different probabilities, or two different distributions with different V's, right? So from the picture, we can see that if the the upper one here, if this distribution has a bigger V, then their ratio is increasing in Z. Okay, so that's how they use this property to make some assumption on the on those distributions. Okay, good. So and what else? And remember that we have some x, so it doesn't matter because we normalize that, and so that we don't need to care about that. Okay, so because we let the expectation of z given v, and we let it to minus x to be exactly equal to vi. Okay, so then in this case we can interpret the signal as the NPV of the project. Okay, so then we don't need to care about this x. Okay, all right, and they in assumption B gave some assumptions on the differentiations and some other properties on the functions. Okay, and we don't need to mention those. Can refer to the paper for that. Okay, so let's have some important definitions. So a feasible security bit, okay, a feasible security bit, okay, this is described by a function as small z. Okay, so and this s is weakly increasing, and z minus sz is also weakly increasing. Okay, and in addition, sz is in between of 0 and z. Okay, and those are very important for some proofs later. And if it satisfies all those requirements, then we call this security bit as a feasible bit, feasible security bit. Okay. All right. So what we are talking about here about those securities is actually we're talking about the steepness, different steepness between them. Okay, so as we mentioned, there are some different kinds of securities that we can use, right? So namely, for example, okay, we have some securities called like the equity, okay, that we used in the example, simply some fraction of the future payoff, right? So as z equals to alpha z. So alpha is just a number between 0 and 1. Okay. And we could use that. Okay. So the seller is promised a face value. Okay. So actually, the bidders, they give this seller a face value D, okay, which is non-negative face value D for this debt, and it's secured by the project. Okay, and we name this as Z equals to minimum of Z and D. Okay, and shortly we will see those. See a picture to illustrate the differences between those securities. Okay, and also there's some convertible debt and levered equity, and you can always refer to the paper. And what we are going to also mention is the call option. Okay, so the seller receives a call option on the firm with a strike price. Okay, K. This K is strike price such that, so we define this call option as SZ equals to maximum of Z minus K and 0. Okay, so the higher bids correspond to lower strike prices. Okay, All right, good. And with those securities, then we can start to analyze the problem. So before that, we need to make some definitions for the expectation of the payoffs of security S. Okay. So in our paper, they use no notation, simply as ES as the expectation of the securities of S. So ES given some V is defined as the expectation. So we don't use that, just E. Okay. ES. So S is a function of Z, and it has to have some conditional distribution given V, right? And that's how it calculates the expectation. Okay, so we always use the H implicitly, right? So that's something hidden here, but it's built inside. Okay, so in lemma 1, they mentioned some pretty fundamental issues. Some results is that the value of the security, which is called the ESV, so this is twice differentiable, differentiable, okay, differentiable, okay. All right, good. So for the S, which is not zero, okay, what we have is that the ES, the derivative of ES with respect to V is positive, and for S not equal to Z, the derivative is smaller than 1, okay? And that proof is not too hard, and you can refer to the paper for that, okay? So those are some very basic and important properties. Okay. All right, so that's some basic definitions and properties. So another use for definition is that, okay, so a function S is a big S and small z. For the small s between S0 and S1. So this big S defines an ordered set of securities, okay? Defines an ordered set of securities. Okay, so if first it has to be a feasible security, right? So we have those requirements before. Is feasible. And secondly, the derivative of ES with respect to S has to be positive, okay? And this makes sense, right? And also it has some requirements with those two extremes, okay? So if S is the smallest, is the minimum, S0, okay, and if V is the minimum V, then this ES has an upper bound, okay? And on the other extreme, it has a lower bound, okay? All right. So this means that for a sufficient range of bids, so that for the lowest bid, every bidder or each bidder earns a non-negative profit, okay, zero or positive. And for the highest bid, no bidder earns a positive profit, okay? So that's a pretty reasonable definition, right? Okay. So normally we have first price auction or second price auctions, right, to be studied. And here we don't need to. We simply concentrate on second price auction, and all the contents regarding the first price auction could be found on the paper. But essentially, they're talking about the similar setup, right? So we just need to concentrate on one and to discuss the details or the results. Okay, so here we focus on the second price auction. So essentially, as we previously mentioned, is that each agent in a second price auction submits a security. Okay, so here it's not a cash; it's submitting a security here. So the bidder who submitted the highest security or the highest S, small s, okay, so that bidder wins and pays the second highest security. Okay, so pays the second highest S, because here we are talking about securities, so we're not paying the second highest cash, but paying the second highest small s. Okay, so we can briefly write that down. So we are focusing on the second price auction. Okay, and each agent, so each bidder submits a security. Okay, and the bidder who has the highest S wins and pays second highest S. Okay, that's the context of the second price auction in this case. Okay, so similarly, because we have shown that in the other episodes, we have shown that the equilibrium for the second price auction is that each bidder bids their own private value, right? So here it's pretty similar, but it's using the securities. Okay, so that's given in their lemma 2. Okay, so the unique equilibrium is a weakly undominated strategies. So it means the weakly dominant strategy. Okay, the same thing. The second price auction is for a unique equilibrium in weakly dominant strategy in the second price auction, second price security bid auction, is for bidder I who has a value of V to submit. Okay, for the bidder I with VI equals to V, okay, to submit the security as V, okay, such that ES of SV V equals to V, okay. And in addition, the equilibrium strategy SV is increasing in V, okay. All right, okay, and that proof is very important, and that's also very interesting, and you can refer to the proof in the paper, okay, and we will not cover that here, okay. All right, and similarly we have some results for the first price auction, right, and that's also discussed in the paper. Okay, so remember that we were talking about the only difference between those two different securities is that they have different steepness, right? So we can here visualize that use a picture, okay? So how do we rank different securities, okay, if we want to design one of those? Okay, so we have a brief picture here, but you can refer to the paper for a nicer one. So this is asset payoff Z, and the vertical is security payoff SZ. Okay. All right. So on the 45-degree line is the cash, okay, which is Z, and the equity. Okay, let me use a different color, or maybe just the black line here. So equity is just a fraction of the future cash flow. Okay. Okay, and for the call option, we have a strike price. Okay. And before that is 0. Okay, and after that it's 45 degrees. Right. Okay. So this is a call option. Okay, and for the debt, okay, so under the face value D, we have 45-degree line here. Okay, let's say it's somewhere up to here. Okay, maybe lower, okay, somewhere here. All right, and after that it's just a flat straight line. Okay, this is that. Okay, so how do we define their differences? Is that steepness. Okay, so they gave a very nice and useful definition on that. Okay, so security S1 strictly crosses S2 from below. And what do we mean by that, right? So that happens if ES1 given some V star, okay, equals to ES2 V star. So it has the same value given some V star, okay. Let's say it's somewhere here, okay, if we're comparing the data and call option. And if we have that, implies ES1 prime V star bigger than ES2 prime V star, okay? Then we can see that the blue line has a larger, has a bigger slope, right? It's steeper than the red, and they have this intersection here at this value, right? Okay, so that means the strictly cross, okay, of S1 crossing S2 here, okay. So, and how do we define the steepness? So an ordered set of securities S1, okay, so this should be a bold S, okay, S1 is steeper, so it should be just a set, right? So it's bolder, steeper than ordered set bold S2 if for all those securities inside of S1, for all S1 in bold S1 and S2 in bold S2. So S1 is S1 strictly crosses S2 from below, okay? And we can see from the picture is that the call option should have the biggest steepness, the highest steepness, right? and after that is equity, and then is debt, right? So we can use this point to compare option with equity, and use that to compare the equity and debt, and use that to compare the option and debt, right? So that's a very useful way to define the steepness. Okay. All right. And the next immediate question is that, so we'll skip lemma 5. Okay. So the single crossing result. And the question is that we want to ask why this steepness is related to the auction's revenues for the seller, okay, or for the bidders, related to their payments, right? So why is that relevant? So we are considering the second price auction, okay, and so in the second price auction, the winning bidder, the winner with type V1, okay, let's say V1, pays the security bid by the second highest type V2, okay, pays the bid, and this bid is made by some type V2. So V1 is higher than V2, okay. So the winner, it means that the winner pays ES of SV2 and V1. So that's exactly what we mentioned in the example, right? So the V1 has their type, but paying the something that V2 bids, right? Okay, so because the bidders, they bid their reservation value in the second price auction, so as the equilibrium strategy, right? So we have that ES of SV2, V2 equals to V2. And this is very important, and we'll use that shortly in some proofs. Okay, so that's something that we know, right? In the lemma 2, I think, that we just show, right? So is there an equilibrium strategy for each bidder to bid their reservation value in the second price auction in the equilibrium, right? So this means that the security design problem actually impacts the revenues only through the differences of those two values, right? Essentially, the difference between ES SV2 V1 and the ES SV2 V2, right? And that is exactly the sensitivity of the security to the true type, okay? That something related to the sensitivity of the true type, right? And later we can show that on some pictures, okay? But after some proofs first. Okay, so essentially, if we want to compare two securities, then we need to compare their slopes, where the expected payments are the same and equal to V2, right? And by the definition we just gave, so the steeper securities, they are more sensitive at the crossing point. So that leads to a higher revenue, okay? All right, so to help us further understand that, so we'll try to show and prove their first proposition, which is pretty important, okay? So before that, let's write that down. So proposition 1. Okay. So suppose the ordered set of securities S1, bold S1, is steeper than bold S2. Okay. So those are two sets. And we have the definition of steeper, that each element strictly crosses the other one from below, right? Then, if we have those, then for either a first or second price auction, we don't bother about first price auction. Okay, we're concentrating on the second price auction, but actually it holds for both. For any realization of types, okay, the seller's revenues are higher using S1 than using S2. Okay, for either a first or second price auction for any realization of types. Okay, so the seller's revenue from the auction are higher using both S1 than using S2. Okay. All right. So that looks very important, right? So now we try to prove that, okay, rigorously prove that, and just using some assumptions or some definitions we just gave in this video. Okay, so let's do that. So proof. So in the second price auction, okay, that which we're only concentrating for now. So in the second price auction, and from lemma 2, okay, okay, and from lemma 2, okay, what we know is that the winner with highest type V1 pays the second highest security bid by the second highest type V2. Okay, pays the second highest security bid by second highest type V2. Okay. All right. Now we have some notation. Okay. So we let S1 to be the security bid by V2 under the bold S1. Okay. Let S1 be a security bid by the type V2 under bold S1. Okay, so that S1 is just an element of that bold S1. Okay, and let S2 be a security bid by V2 again. Okay, so notice that those are both V2, and S2 is under the bold S2. So careful the notation here. Okay, so both S1 and S2, they're just two securities. Okay, so those S1 or S2, they have nothing to do with the bidders, one or bidder two. Okay, so those are just two kinds of different set of securities. Okay, okay, so we have some, we should write this down. S1, S2 are just two sets of securities. Those both are some bids by V2, right? Both by V2. Okay, so there's nothing related with V1. Okay, so that's something very important. Students should be very careful about. Okay. All right. So because ES in the second price auction in the equilibrium, we know that ES as VV is V in the equilibrium of the second price auction. Okay. And that should be true for any set of the securities, right? So it doesn't matter what this bidder is using, right? So it doesn't matter if it is like equity or it's debt or call option. It doesn't matter. So in any form of in any kind of securities, this this value should always be the same, right? Which is the this V2, right? So now we're looking at the V2 here, okay, for now. So the V2's bits should be always equal to V2, no matter it's using S1 or using S2, okay? So that's the meaning of S1, S2. Here, there's nothing to do about or to do relevant to bidder 1 or to V1, okay? So here we're talking about V2 all the time here. Okay, so that's something we have for now, okay? So, and again, since S1 is steeper, right? So that's given is steeper. So S1, all the elements in S1 strictly crosses S2. S1 is steeper than both S2, then the edge element in S1 strictly crosses S2 from below, right? Okay, so this means that ES1 V1 must be bigger than ES2 V1, okay? And why is that? Okay, why? So this is because, okay, remember that V1 is the highest type, right? V1 is bigger than V2. Also, and what we have from above is that ES1 V2 equals to ES2 V2, right? For any bidder, of course, including bidder 2, that what we have is that no matter what kind of security, S1 or S2, each bidder always has the same bit in the equilibrium, right? So equal to their private value. Okay, and because again we have this steepness, right? Because S1 strictly crosses S2 from below. Okay, and we have V1 is bigger than V2, and ES1 V2 equals to ES2 V2. So, sorry, because we have V1 bigger than V2 and ES1 V2 equals to ES2 V2, okay? And what we also have is this, right? So we have this, this, and this. Then all those together, we can have this. And this is pretty straightforward. If you simply draw a picture, okay, and you can notice that from those assumptions or those conditions, you can derive this result, okay? So let's suppose we have some equity here and some co-option here, okay? So for V2, okay, it's saying this equation here, right? For V2, this value, no matter which security is using, V2 is using, then they have the same value of VS, right? Because V1 is higher than V2, okay? Then it must be that with this steeper security than this value, given V1, it has to be higher than the value under this less steeper or flatter security, this, right? So this point has to be higher than this point. So that's something that we have proved, right? Okay, so now what we have, let's label that. So if we say this is number 2, okay, and this is number 1. Okay, so number 1 and number 2 together, what we have is that use 1 and 2 together, we can simply get ES1V1 minus ES1V2 is greater than ES2V1 minus ES2V2. Okay, so this is simply obtained from 1 and 2, right? We just use the use 2 to minus 1, right? And that's it. So, and what does this mean? It means that the left hand side here, this is nothing but seller's revenue, okay, from using S1, okay, and here is seller's revenue from using S2, right? So here we can then simply observe that if this S1 is steeper than S2, then the seller can obtain higher revenue using using the steeper security here, right? Okay, good. So that's the proposition 1 is very important, and also this result is also very useful, right? Okay, and as we mentioned, we can not only have some results on the formal auctions that where the seller assigns or the seller designs some kind of a specific kind of security, right? It might also happen that the bidders, they can actually choose from a set of the different kinds of securities, right? If that's the case, then that would be called as informal auctions. Okay, and actually, DeMarzo et al. They mentioned that in their in one of their section 3, I think, and called informal auctions the signaling game. Okay, so in that part, they introduced some even some more interesting results given that possibility. Okay, and if we have chance, then later we can discuss that also and to show some more interesting results. Okay,